Our next speaker is Larry Denneau. He's been a computer guy since the early 80s, done a wide range of things. Larry and I both worked in the semiconductor industry for a little while back in the past. He got his bachelor's degree at University of Arizona and a PhD from Queen's University, Belfast. And he's on the Atlas team. He'll probably explain that a little bit and talk to us about the DART mission.
Okay, thanks, Kurt. So the Atlas project that I work for is a planetary defense project. And what that means is, let's see, there we go. Planetary defense means protection of the Earth from hazardous asteroids. We're not protecting against space aliens or UFOs or anything, but asteroids are what we care about. And I'm going to tell you about planetary defense and a thing that happened last year called the DART experiment. It was in the news a lot in late September when it happened. And DART is actually an acronym that stands for Double Asteroid Redirect Test. So maybe not a lot of people know what the acronym stands for. It's kind of a weird name for a project. If you've been following planetary defense over the years and you watch movies, maybe you think planetary defense is just blowing up an asteroid that's coming at the Earth. So, you call Bruce Willis up, you send him out, and he deals with the problem. In reality, planetary defense is a lot more complicated. So you don't have to memorize everything on this slide, but by the end of this talk, I think you will understand everything that's on there. So we'll just plow right ahead. Okay, so planetary defense is protection of the Earth from asteroids. There's actually an office at NASA called the Planetary Defense Coordination Office. They fund us, they fund other projects like us, and a whole spectrum of things that are involved in the detection and mitigation of hazardous asteroids. If you know a little bit about asteroids, you know that they mostly live in orbits between Mars and Jupiter. But what this diagram shows are about 35,000 known near-Earth asteroids. So those are asteroids that have orbits that bring them into the inner solar system, into our neighborhood, Venus's neighborhood, and every once in a while, those asteroids can hit something when they're in there. So those are the ones we care about, and those are the ones that are hazardous to us. Now, in human history, we know that there are things on the Earth that are evidence of asteroid impacts. The meteor crater in Arizona, the Tunguska event in Siberia, a couple of other craters that weren't identified until there were satellite photos of them. And then most famously probably is the Yucatan event, which is the event that killed off the dinosaurs, about a 13 kilometers, so the 8 or 9-ish mile wide asteroid landed in the Yucatan, and that was the event that caused the end of the dinosaurs. A little bit more recently, in 1994, a comet called Shoemaker-Levy 9. So Shoemaker, Gene and Carolyn Shoemaker and their partner David Levy were astronomers, discovered a bunch of comets. This is one they discovered in 1993. And the unusual thing about it was that it had broken up into a bunch of little pieces. And after they discovered it, they realized from observing it for a while that this comet was actually captured by Jupiter. And the next time around, in Jupiter's orbit, it was actually 100% going to hit Jupiter. So this was a really unusual event. It was really exciting because it was the first time that it was predicted that two bodies in the solar system could collide. And lo and behold, in 1994, the collision happened. And so these bright spots on Jupiter are those individual comet pieces striking Jupiter as it went by Jupiter. And here's Earth to scale, so Earth compared to Jupiter, tiny. So these big spots, these big impact blows are the size of Earth. So that's how much destruction a single comet is capable of if it were to hit another body. So in 94, that turned these, what we believed were like ancient cosmic events into something that we realized could happen in our lifetime. And then much more recently and much closer to home, we have things like this. So here's a random YouTube video from Sri in Thailand. There's a small meteor going through the sky. In 2013, there was an event in Russia over the city of Chelyabinsk. This was about a 20 meter, so house-sized rock that exploded in the atmosphere. And even though the pieces of the rock, basically, the rock didn't make it to the ground intact, but the shock blast as it exploded in the atmosphere, what happened was the flash happened, everybody ran to their window to see what it was. Light gets to you much faster than sound. And so when they got to their windows, the shock blast blew windows in, and about 1,000 people were injured. Nobody was killed, fortunately, but It did a lot of damage and a lot of people were hurt. And here's where a small piece of it landed in the snow. So this is maybe a golf ball sized piece of something that has so much energy that it made a hole that big in the snow. And then just last year, a very small asteroid about the size of a garbage can was detected in space. So that's why it has an asteroid name 2022 WJ1. But it was detected a few hours before it hit the Earth, and we knew exactly where it was going to land. And it went over London, Ontario, so a little north of Detroit, and we knew down to the minute when it was going to happen. So we called our Pan-STARRS colleague Rob Merrick, who lives there, and said, "Hey, at like 4 a.m., go outside, point your DSLR up in the sky, and this thing's going to happen." And there it was. So that's pretty amazing, right? That's how good we are now at detecting some of these things and telling you when and where they're going to hit. Fortunately, this was a tiny one. The ones we care about are much larger. So now that we know asteroids can hit us, and they can hit us on timescales that are relevant to us, might happen in our lifetime, NASA has formed this Planetary Defense Coordination Office. I'm not going to go through this whole thing, but basically what I want to show is that NASA is thinking hard about this problem. And the IfA is involved in this part up here, which is kind of the initial part of the whole stage, which is to search, detect, and track these things. You can't do anything about them unless you know they're there. So the first job is to find them, and that's what we do. After these things are found and their orbits are determined to be hazardous, then other things come into play, and if it's believed that the asteroid will hit, then a whole series of other things like civil defense, FEMA, the UN, all of those organizations get involved to move people or to move equipment or to think about some kind of space-based mitigation. And that's what we're going to talk about next. So if you know an asteroid is going to hit the Earth and you have some warning time, what are the things you can do about it? In the movies, and it's not impossible, one possibility is to blow it up, to send some nukes out there and try to blow the asteroid to smithereens. That's technologically not as easy as it may seem, because you don't want to strike the asteroid. You actually want the bomb to go off just off the asteroid to maximize destructive effect. And we're not sure that we can do that at the scale we would need to do to completely disrupt an asteroid. It's also politically very, very difficult and sensitive, because there's no country that's excited about another country putting nukes up out of space. And so the way to navigate that problem has not been settled yet, but it's an option as a last resort. If there's nothing else we can think of and all of humanity is at stake, we would certainly consider that. On the other end of the spectrum, there's a thing called a gravity tractor. And what that is if you park a spacecraft next to the asteroid and you just keep it there, because the asteroid is going to attract the spacecraft very closely. Your spacecraft has to have a little bit of propulsion to stay off of the asteroid. But over decades, this spacecraft will drag the asteroid ever so slightly into a different path that 20 years down the road would miss the Earth if it were on an Earth-hitting trajectory. So that's one option, but it takes a long time to work, and the mechanics of how to do that have not yet been worked out, and it's very difficult to test because it takes so long to happen. So that leaves us with something in the middle that we call a kinetic impactor. And what that means is that you smash the asteroid with something, not intending to blow the asteroid into lots of little pieces, but to just give it a nudge. And that nudge, hopefully, is enough to change the path that this asteroid is on so that it doesn't hit the Earth, but instead just goes by the Earth. So a few years ago, NASA came up with this experiment called the DART experiment. So this is the double asteroid redirection test. And it's a test of a kinetic impactor concept. But why the weird name? What's the double asteroid part of it? There's a scientist at Johns Hopkins who's on the DART team, and he had this great idea. So one problem with a kinetic impactor test is it takes two spacecraft. You've got to send up your spacecraft that's going to hit the asteroid. Then you need another spacecraft that's up there watching the whole thing to see what happened. And it's the government's money, so NASA, is conscious of how much it costs to do these things. So if it can avoid it, it doesn't want to send up two spacecraft. It's much better to send up just one. And so what Andy Chang at JHU figured out was that, hey, this asteroid called Deimos, it's a binary asteroid. So here's a radar picture of the asteroid. So these are different pictures of the asteroid going to left to right. And this thing here is the reflection of the asteroid. So you can see one side of the asteroid. But this little dot that you see up here, that's its moon. So this asteroid has a small moon. The main asteroid is called Didymos, and its moon is called Dimorphos. And what Andy suggested was that if you hit the little moon, you don't need to send another spacecraft up there to look at what happened, because from Earth, we can tell how the orbit of the little moon changes around the asteroid from the ground. So it's a big savings in terms of the cost of a mission. You only have to send up one spacecraft. And so everybody examined this concept. They decided it's a good thing to do. This asteroid was in the right place, the right time, at the right cost. The science and engineering aspects of it were all feasible, and so they decided to do this. And so there was a couple of scientific objectives that they wanted to understand. One thing is that we don't know exactly how these asteroids are put together. So this gives us a chance to do that. Right? We can smash something into it, into Dimorphos, the moon, and look at what happens to it when we do that. That'll tell us about how the asteroid is built inside. And we don't know whether, in general, they're very solid, or whether they're kind of spongy with like what are called voids inside. And the problem with voids is that they absorb the impact if you hit them. And you want your impact to have maximum effect, right? So that's one thing we want to know. And there's this other effect called this recoil effect that astronomers call beta. And what that means is if you hit your asteroid with an impactor, all of the stuff that comes out of the crater in the opposite direction, and we call it ejecta, that the amount of ejecta that comes out is this amplification of your initial impact. So you get like more bang for your buck if your asteroid gives you more beta. And so one of the things we wanted to measure from Dimorphos, the moon we were going to hit, was what is this beta number? Because if you have large beta, you don't have to send up as large a kinetic impactor. You can have a smaller object. Smaller object means faster launch, lower launch costs, and so on. So it's better to know what that is and know what your design goals are for when you have to do this for real. And then the fundamental measurement of how much did we nudge the moonlet, Dimorphos, is going to be measured by how long does its orbit take to go around Didymos. And before the impact, it was pretty accurately measured to be about 11 hours and 33 minutes, I think. And the hope for the experiment is that that number might change by plus or minus 10 minutes. That's what they're looking for. So you'll find out later in this talk what they found out. Okay, so just to give you some idea of sizes that you can relate to, Didymos, the main asteroid, is about yay big. It's almost a mile across. Dimorphos, its moon, maybe about the size of a football field or a couple of football fields across. So they don't sound big until you look at them kind of on this scale, and they're pretty sizable rocks, right? And so the DART spacecraft itself, it's not a big thing. It's about the size of a Coke machine, actually, going 15,000 miles an hour. But that's all it is. And that Coke machine going that fast can't make an effect, a measurable effect on this orbit. So here's the schematic of the whole setup. So here's the DART spacecraft. It's really just a box about the size of a Coke machine or a refrigerator. It's got some solar panels. DART was launched as late as in 2021. It was a very quick mission. So you know how if anybody was here for Karen's talk, she said NASA moves very slowly. The DART mission actually was put together and launched quite quickly. It was only like 9 months from launch to arrival at Didymos. Attached to DART was another CubeSat called Licia Cube, and its job was to simply fly by Didymos, actually Dimorphos, at the time of impact, and take all of the pictures it possibly could. And it only had a few minutes to do that, but it was an opportunity to very cheaply try to film what was going on at the time of impact. So this is the setup. Dimorphos, the moon, orbits in this diagram around Didymos this way, and we are going to hit it head on in the opposite direction that it's going. And so that energy imparted will slow down its orbit. When its orbit is slowed down, it'll move in a little bit closer to Didymos and have a shorter period going around. And that's that shorter period that we're hoping to measure to tell us what effect we had by hitting Dimorphos with this impactor. So a little bit to scale. If there are any kids are here who are into Lego, you can go down to the Lego thing and make one of those. If you make one of those and tell me about it, I'll give you a sticker. But I don't see any kids here, so anyway. The real spacecraft looks like this. So there is solar panels. This camera is called the Draco camera. This is a super neat feat of engineering. It's used to actually take pictures of the asteroid as we're approaching, but it's also used by the navigation system. So that camera it tracked on Didymos, the big asteroid, millions of miles away, and it just locked onto that all the way to the impact. And so there's really neat software on board that can navigate the spacecraft, looking at the stars and looking at its main target and get us there. And to me, that's, as a software engineer, that is an amazing feat of engineering. So what happened? So this is the date of the impact. This is the last maybe 10 minutes of the DART mission as seen from the spacecraft. So for weeks before, it was locked on to Didymos, and now it's close enough to see Dimorphos, the moon. And so it's locked on that. And this made the rounds on YouTube and everywhere else on the internet the day that it happened. And I think from I watched it live and we were all whooping and hollering and just amazed that this could happen. So the last few images are slow to come in because I think the instrument is freaking out, and that's the last one that's glitched, but it's, you know, just before it hits. Those boulders on the second to last frame are probably car sized. I mean, that's how close it got and how well it was resolved. So that's pretty cool. The Licia cube, CubeSat that flew by, this is what it saw. So think of it as starting kind of to bottom left and flying up into the right. I guess it's the opposite way because of the background for me. So here's Didymos, the main asteroid, and here's Dimorphos right after the spacecraft hits it. So you can see these dust plumes being just, you know, dust being just liberated and excavated from the asteroid and then sent all over the place. So the project I work on, Atlas, is a ground-based telescope. We all knew this was happening. We knew down to the second when the impact was going to happen. And only our telescope in South Africa was capable of witnessing the event because that's where it was dark and it had like excellent observing geometry. And fortunately, the weather in South Africa, our telescope is, it's not the best place to put a telescope. And so the weather is always a little bit sketchy. But on this night, the weather was completely pristine. And this is what we saw. So there's the big dust plume from the, you know, the poof of the impact. This is about 2 hours of events crammed into about 5 seconds there, right? So that's not in real time. But for us on the ground, I think the predictions were that we would not see anything like this at all. We would just see this white spot kind of get bright and then get dim. And to see dust and dust that has structure was amazing to all of us. And so we sent this to our NASA program manager right after we got this data. And they were passing it around their control room. Did you guys see this? It's amazing. And you know, we got press inquiries from the New York Times and from BBC and stuff who all wanted to run this photo or this animation. And it's pretty slick. So we're scientists here. We wanted to, you know, we want numbers, right? We want to characterize our results with numbers. And so what did we learn? So the orbital period of Dimorphos, the prediction was maybe 10 minutes of the reduction of the period. We got much more than that, 33 minutes. So that's a big change in orbit. And what that means is that this beta number, this recoil factor, was bigger than predicted. So this number 3.64, if you want to round it, means that the geometry and internal structure of the asteroid gives us this ejection factor that produces this enhancement from our impact that's a factor of 3 to 4 bigger than if there were no ejected at all. So that's awesome. So an asteroid of that size that is of similar composition means that we can possibly use a smaller impactor to get a desired effect. This number, from what I've read from some of the papers, is a little bit, it's probably higher than this, but this is a conservative estimate of what that number is. So those are some specific scientific objectives that were measured and met. And we had our few moments of fame. Let's hope this works. We make that. Try it again. Okay, let me go back. It's such a fun clip. I have to play it. Say when. Okay.
Sorry. I can't figure it out.
Can you mute your mic for a second?
I can. Let's see here. Turn it off. Where is it? Where's the button? Okay, I'm gonna turn this off. Is that off? Let's see if this works. This might work. Sorry. Anyway, Colbert loved us. He said we saved the world. I'll skip. Okay. Anyway, DART headquarters, high fives. Everybody loved it. And this is quite a bit later, and a beautiful image of the Dimorphos, Didymos Dimorphos system, long after the impact. The dust that was liberated from the impact still hanging around and making this nice comet-like tail from the asteroid that's still there. So even our Atlas telescope can still see this. I mean, it's amazing that the dust is it was released from the asteroid very slowly. There's very little gravity. It's being pushed back by the solar radiation, and it's just taking a long time to go away. And it makes this beautiful new comet. So that's the DART experiment. What have we learned? What's next? Well, one thing that's next is the European Space Agency has put together a mission called HERA. And HERA's goal is to go look at what happened in great detail. So HERA's not going to launch until 2024. It won't get to DART. I'm sorry, to Didymos until 2026. Nothing up there is going to change. It's out in space. There's no weather to change anything. It's all going to be just like we left it. And so what they expect to see is a crater that might look something like that. The main HERA spacecraft is going to launch 2 CubeSats to wander around the asteroid and do all kinds of characterization to look at the surface, to try to look under the surface, and so on. So that's going to be another gold mine of scientific data that will help us understand this particular experiment, but what asteroids that are that size, how they might behave to another kinetic impactor. In terms of big picture to how dangerous are asteroids in general to Earth, this is kind of like when NASA goes to Congress and talks about what's out there, what do we have to worry about. This is what they show. And this is basically a snapshot of the near-Earth asteroid hazard that's out there. And the stuff in the red box is really what we care about. The biggest things that are out there are 1,000 meters and larger. They've all been accounted for, except for this little tiny slice here, which we'll clean up in the next 5 to 10 years. And down here, these are all small asteroids, 10 meters and smaller. So they're not big enough to be dangerous. But the stuff in this red box, 50 meters to say 140 to 300 meters, those are things that we don't know where all of them are. At the 140 meter size, we barely know where about just over a third of them are. And at 50 meters, we're at like 5%. There's a ton of those still out there, and we still got to go find them. And these, if they were to hit over a city, could do regional or larger damage. It can cause a tsunami that could impact millions of people. So this is really where the focus is now in planetary defense. And so modern planetary defense surveys like Atlas, Pan-STARRS, and so on are now trying to, as fast as we can, catalog asteroids in this size regime. So next steps are to just continue looking. So Pan-STARRS 1 and 2 that are here at IfA and on Haleakala are operational. They're a very significant near-Earth asteroid discoverer. Catalina Sky Survey in Tucson, Arizona is another one. Atlas, my project focuses on, we're not the biggest discoverer, or we don't discover the most near-Earth asteroids, but we specialize in discovering ones that have sort of slipped through the net and are on a final impact trajectory with Earth. And we find a lot of small, close approaches, as we call them. We have detected 2 asteroids that have hit the Earth. They've both been tiny, fortunately, but our job is to kind of be the observatory of last resort, let's call it, that finds them, these that slip through the cracks, and provides warning for a civil defense kind of reaction to an asteroid impact. The NEO spacecraft is still out there observing, and it's also a contributor to near-Earth asteroid discoveries. Coming up, we have a huge telescope in Chile that's being constructed. It's almost ready to turn on. The Vera Rubin Observatory. It's going to observe for at least 10 years, and it's going to find more near-Earth asteroids than all surveys up until now have ever found. That's how sensitive that telescope is. And we're hoping that in 2028 or so that another space-based telescope called the Denneau Surveyor will launch and will also do another great job at finding these things. So we're hoping to get that 140-meter catalog completed much faster than we did the 1,000-meter kilometer catalog by having all of these assets out there looking for stuff. Another thing that's coming up is there's an asteroid called Apophis, which is a pretty sizable asteroid from the figure there. It was discovered by the IfA's own David Tholen. And this asteroid has been significant for a few years. And one thing that we know about it is going to make a very, very close approach to the Earth on Friday the 13th in 2029 in April. And this approach by Apophis is going to change the orbit. It's going to come so close to the Earth on that day. And for a long time, we did not know whether, when it came around again in 2036, whether it would hit the Earth. It was an open question. And now it's a closed question. We know it's not going to impact in 2036. So we can take a breath there. But this close approach was very, very important in knowing what was going to happen as it came around again. So this thing is going to come almost inside the geobelt of the satellites. That's how close it's going to come. It's a really big thing that's going to come through there. If it were to hit a satellite, which is below it, completely to smithereens. It's a big object. It's uncannily like, if you saw the movie Arrival, the things that came from the aliens, but it's not that. Anyway, I just love that picture. And so here's a little animation of like the event in 2029. It's going to happen. So Apophis is the red X, Earth is the white dot. They come very, very close to each other. And if you were standing on Apophis during that encounter, here's what it would look like. Let's see here. Oops, sorry. Let's see if this works. Let's see, should start. There we go. So that's Earth in the middle. We're standing on Apophis as it goes by the Earth during that encounter. There it is. Boom. That's the moon, the other bright thing. So anyway, so this asteroid is going to come very close to the Earth, but it's not going to hit. But coming that close, it's another opportunity to study the asteroid. There's going to be spacecraft missions that go and examine it. We're going to do radar measurements of it. Anything we can think of to like find out more about asteroids of this size, because those are in the sweet spot of the things that are left over to find. Right, Apophis is a perfect example. So, in the scheme of natural disasters that are out there, earthquakes, hurricanes. That's Mauna Loa erupting. So, in fact, Atlas has a telescope, we think, still on Mauna Loa, and but we've been cut off from it since November because the lava has crossed the road, the access road to the summit. I think there are sections of lava, Doug, it's like 30 feet high, right? I mean, it's huge, and so we still do not know when we will be able to get up there next, and what the fate of our telescope is going to be. We may be able to turn it on in a few months if we can get some solar power things going our way, or if that doesn't work out, it may be years before the road and power are restored all the way to the NOAA station where our telescope lives. So volcanoes do happen, and here's the Chelyabinsk meteor from 2013. So the difference between an asteroid impact and all of these other events is that it can be predicted very accurately when this will happen, and we can actually prevent it. We can't prevent a hurricane, earthquake, or a volcanic eruption, but we can, with enough advance notice, prevent an asteroid impact. And if so, we can all take a breath and relax. That's all I've got. Happy to answer some questions. Thanks.
You said between 30 or 40% of asteroids are known. How do you have those known unknown amounts of asteroids where you can estimate that 40% are known?
So as an example, so if you notice the 1 kilometer sized column, if you look at the discovery rates of those over time, you can see that we discovered a bunch every year, and basically that has fallen off. So there's no more of those out there. So that's how we know if that column has basically been satisfied. But the right way to do it is you come up with a model, a synthetic population of asteroids that may or may not be the real population of asteroids. And then given all of the asteroid surveys that have ever operated, you, through a computer simulation, measure how many of those asteroids would have been discovered by any of these surveys, by how sensitive they can see, how they observe, what their observing cadence is, what their weather is like. And from what they find, then you can back out what the population should be. And did you get your original population out? So there are ways to model what the population could be, and you observe and ask yourself, based on what these observatories are capable of seeing, can you reproduce that population? You iterate on that until you get something that you think is likely to be the real population. So the many decades of study have gone into what are the populations of asteroids out there, how close are we to satisfying them? And one thing you can look at is the current discovery rate of asteroids. Is it in line with what we think the populations are? And the answer is basically yes. So they can be off by even a factor of 2. In astronomy, that's like almost on the money, a factor of 2. But we know that, it's not going to be much larger than that. So for example, I think the number of 50-meter asteroids is something like 230,000. That number might be 400,000. It might be 300,000. But it's in that ballpark. It's not 5 million, for example. Another question back there.
Yeah, so if we were to predict Apophis hitting us in 29, what would be the proposal? If you try to intervene it while it's far out, it's far. I guess if you hit it far enough away, you just divert it a little bit. That works better than when it's close.
Absolutely, it's exactly right.
So that's what we probably do, right? We try to
2029 is pretty close. I think at that point, with an object of that size, you're looking at some kind of last resort kind of thing. It's not enough. So to nudge an asteroid, time is your friend, right? You need more time. And so a decade out to give it that nudge, that little nudge then becomes something large a decade later. Apophis is, I think it's right around the corner. It's like one orbit away from coming. It's, we're 6 years from 2029.
Yeah.
So it's on its next approach. And so you basically, if it were to hit, you have one shot at it, and so you throw everything you can at it.
Yeah, it was something really.
Yeah. So there's a meeting called the Planetary Defense Conference that's held every 2 years, where there's a tabletop exercise involving astronomers, NASA, JPL, FEMA, the UN, all of these stakeholders get in, they work this week-long exercise that's constructed to focus on different elements of mitigation. So observing, characterization, a hypothetical mission. It usually fails because you need to get to the next step. And they think about exactly, what you would do if if one of your things to mitigate didn't work out and you're down to a last resort. So, and something like one of these last resorts, one thing that comes into play, for example, is that when it's going to impact, it's going to be along a really narrow corridor on the Earth. So think of like dropping a string on a globe. That's the impact location along that string. And most of that string usually will go over the ocean somewhere, but it'll go over land. It might go over a big city. And at that stage, you're worrying about, if we're trying to nudge the asteroid, but we're unsuccessful, could we nudge it into another country that it would not have hit originally? Things like that, right? That kind of stuff comes into play, and it's stuff that has to be thought about, when you have countries trying to cooperate to solve a problem like this. So there's just beyond, is it going to impact? There's all of these kind of secondary questions that you have to think about, and it takes people and cooperation to settle some of that stuff.
And what about the movies with explosions? Is that a thought at all?
I'm sorry,
The idea of an explosion, a nuclear problem. Is that?
Well, there's a lot of Cold War nuclear scientists who don't have a lot to do now, and so they think about this kind of thing. And it's absolutely possible. So putting nukes in space is not an easy thing for countries to decide on how to do. And if it's the US doing it, a lot of countries might not be so excited about it. But if the problem were posed as, humanity literally is imperiled here, then I think there's a way to get to that solution. If it's not all of humanity, if it's one country that is kind of in the impact path, then putting nukes in space is maybe not so easy, you know, so it's, every situation is going to be different. In the back.
Last question.
What would be the results of a comet impact, and are all asteroids about the same density?
So comets are a great question because that table that I showed, these are all asteroids that we're talking about. These are things that are orbiting the sun, that are generally between, you know, Mars and Jupiter, but have paths that bring them into the inner solar system. Once, let's say that we found every single one of these that are out there. Comets are then the remaining sort of unknown risk that's left to the Earth, because comets come from the distant Oort cloud, and we don't see stuff out there. There's a huge number of them just floating out there at the very, very edge of the solar system. These things get nudged toward the sun by some interstellar gravitational event, like a passing star nudges these toward the sun, and then they take thousands of years to come into the inner solar system. And if they don't hit anything, then they go back out and we never see them again. There's always going to be a small number of those every year that are coming in and going out. And the odds are small, but they're not zero, that one of those could hit the Earth, and it's probably happened in the past. So comets are, once all of this is done, let's say decades from now, will remain I think the dominant unknown factor out there for planetary defense. And comets, these Oort cloud comets can be quite large. They're not as dense as a rocky asteroid in the main belt, but they're big. And we, they're all going to be different, right? So I couldn't tell you how big any particular one's going to be. We'd have to try to measure it and hopefully see them when they're very, very far away, like out past Saturn, Jupiter, so that we have years to do something about it. But as comets are a great question.
Everybody.
Thank you.
We have one more.